Here is a quick overview of how I configured this 2500 watt ZVS style induction heater that I got off of Amazon. You can find these on eBay everywhere. Quality is, all right, nothing great. It comes with a really good power supply. I have a feeling these were taken out of old telephone equipment or something like that. This is a 48 volt power supply, 50 amps. Buying just this alone is quite expensive, but when you buy it in this kit, I think it was $200, something like that, for this and the power supply. It comes with a little circuit board that plugs into the back of the power supply that's got your hot lines and your 48 volt lines. The circuit connectors, or the spade connectors, are pretty small, so the current capacity is higher than I think these things are really designed for. But I just doubled up on some 10 gauge wire for the 48 volt side. And then I'm using 220, so you could do 110 and get less power. I think you would maybe need to boost that up to like 200 with a transformer or something, but I've got 220 available. So instead of hot and neutral, I've got my two hots and ground, and then 48 volt. The wire, pretty much. I add some other stuff here, but you don't really need that. That goes to a switch, basically, which is a breaker, and then comes into the induction heater. And there's two fans on here. These run off of a 12 volt circuit. It comes with a little power supply, 12 volt power supply, that'll control that, and also a water pump that lets you pump water through the coil, which is just 3/16 aluminum tube, copper tubing, something like that. I made some modifications. Normally this coil would attach directly over here with just some standoffs. It's kind of a crappy little attachment mechanism, but I added some extension wire. That wire can get kind of hot. This is two 6 gauge stranded copper wires that are, less than 3 feet, but around 3 feet long. And they'll warm up when you start really pumping the current through there. But the coil stays pretty cool with the water running through it. So that 12 volt power supply runs the fans and the pump. So you can just use the one they have, plug it into a 110 outlet, and it'll be fine. Like I said, though, I made some modifications. So one of them that you just saw was I put the coil on some leads so I could have some mobility, and I actually wanted to get all the water and stuff away from all this circuitry. So that's going to mount in a different spot, and I might just leave it free and use it with my hand to put around when I'm heating up, which are heat shrink tool holders for the CNC machine. But you could heat anything with these, and it works pretty good. It's pretty quick. The coils need to be a certain size. If you make them too small, then the inductance of the coil is too low, and you get too much current running through the circuit, and it'll get really hot, and this stuff will pump out too much current. So you got to be careful on coil size. It's better to have a coil that's closer around what you're trying to heat. So as you can see, this has a pretty small diameter, and that coil is pretty big, and that's not very efficient. So smaller tool holders, I might make a separate coil, but again, I can't make it too small because it'll draw too much current and overheat. That's something to play with. So the cheap Chinese induction heater that we get off Amazon, it works the way it is. You don't need any extra equipment. You plug that coil right into here. That's what I was doing before. Works fine. But there's a couple of caveats. The power supply that this one comes with, it's an Emerson, I don't know what the model number is down there. So it's a good power supply, but it takes a few seconds to come up to power. And so the voltage, it probably takes about 15 seconds to get up to 48 volts. And you cannot put power to the induction heater until this thing is up to voltage. So you can just, wait and then flip the switch. It's going to have, control current going into the heater. Or what I did is I got a little timer. So I got a separate 12 volt power supply that's running off of the AC line, the 220 volts again. So I'm not using their little cheap plug-in one. That 12 volt supply powers the fans and it powers the pump, but it also powers this timer, and then it also powers this relay. So this is just an automotive 50 amp, or no, this is maybe a 100 amp relay. And I've got from the timer, when this goes approximately 20 seconds or 30 seconds, it then turns on, sends a 12 volt signal, which I have running through the relay back into ground to turn on the relay. That adds a level of safety for me so I don't forget, and I don't want to blow up this power supply, which would be very easy to do if you get if the voltage is too low when you turn on the induction heater. So I just kind of made it a little bit more idiot proof. And then I also added a breaker to the mains power. So this is a 2-pole breaker since I'm doing 220 volts. And I'm taking it from the wall into the breaker. That goes into the power supply. Then that same power I've got into a little bus here. Got too many positions on it. It looks more complicated than it is. But I'm just basically using this as a jumper to get the AC power now to the 12 volt power supply. So it's pretty simple. If I ever put anything else on here, I'll have, that power right there if I need it. Then once we go, this 12 volt power supply runs the timer. So basically when it gets AC current to it, it starts the 12 volt supply. When this gets the 12 volt or the AC current to it, the 12 volt current to it, it starts the timer, which is adjustable. And then that timer, after 30 seconds, turns on this relay. And now we have a connection to the heater. I still have this power switch on, so it can turn on. Like this can be after 30 seconds, it completes, turns everything on, this relay's on, but the switch is still off and it won't power the heater. So I've got two ways. So I could leave this on and then turn on the main power, then 30 seconds later, the heater would turn on. Or I can leave this off and just use it when I'm ready to actually heat something up, flip that switch, and we're ready to go. Another good thing about having this relay is I can now use different kinds of switches. I might put a temperature probe on to control power going to the heater. I don't want this heater to overload, so there's some tricks we could maybe do there in the future. I don't want to get too complicated. This was supposed to be kind of cheap and easy. I've already made it a little less than cheap and easy, but this stuff is pretty affordable on Amazon and other places. I just liked having it all on a DIN rail. So the DIN rails make it a little neater, but it doesn't have to be that way. There's other ways to do this. Same kind of thing, relay with a timer, turning on, allowing current to flow to the heater. So that's pretty much the broad overview of it. I've seen a lot of other versions of this, and I don't think anything's better or worse. I do like that this is a little bit more idiot proof. I've got to kind of cover up some of these wires better so no one shocks themselves. But that should be pretty effective. I've also added a current meter. So this is a power meter. There's a shunt in here that's a resistor, and it's pretty cheap, something on Amazon again. That'll show us how much the voltage is coming off of the power supply and then how much current is going into the heater. This is a good thing to keep an eye on. So if I just turn the heater on with nothing inside the coil, it's drawing around 7 amps. So a good current flow going with nothing in there. If this was a little bit bigger, more turns on the coil, then it would be lower current. Until you put something in there and start heating it up, then the current starts shooting up. And so I like to be able to look at that meter and determine if I'm having too much power going into the system and things are getting hot. So this will light up and tell me voltage, current, total watts. It's cheap and works really good. This is a 50 amp shunt, and that's going to be around where we peak. So I probably should have got a 100 amp shunt, or if there was a 75. But again, this was just an add-on to give me more information so I could be a little bit more intelligent about how I'm powering things. So when we do these heat shrink tooling, we don't want to overheat this holder. So keeping an eye on power and time is one way to make sure that doesn't happen. I'm thinking about how I can add a temperature measurement in. So we could measure the temperature of the water coming through the coil because it's getting heated up. But I think I could probably manage to mount a little thermocouple, just like clip it on and have a direct measurement, and then have that, like I was saying earlier, go back to shutting off the relay when it hits, 500 degrees or something like that. And that should be enough to be able to remove the tool, put it back in, whatever. So I don't want to, that's the professional shrink fit holder, tool fitting heaters. They kind of, you can't overheat the tool. So that's kind of handy. So when it comes to the coil, like I said, I added this extension cord. This is two 6-gauge wires, and these will still get pretty warm when I heat up something. So you can get water-cooled cables. AliExpress has some that are for the bigger induction heaters. I think this is going to be fine for my purposes. And you don't have to have it on there. Most people leave the coil directly in here, and they might have this on sliders, and so they can move it in and into their tool holder. But I like this flexibility to get things out of the way. Then I added to the copper tubing just some plumbing so that I could put in the water in a different location. I didn't like coming into the back here with the water. They just had tubes slip on. I wanted some quick connect tubing and then just something that felt a little bit more waterproof. I ended up adding some copper tubing on the back here. That kind of seals this up, and I soldered the tips of it. I squeezed it and soldered it. I bet you I could have just squeezed it and folded it a couple of times and it would have sealed up, but I went ahead and soldered it. Then these two lugs where power comes in, these are just electrical lugs. I think they're grounding lugs, something like that. Again, I think it was like $6 for two of them on Amazon, but it's kind of a convenient way to hook it all together. And then this quick disconnect tubing I really like, and I'm not sure how I'm going to do the plumbing yet. I want to have this a lot cleaner and not open buckets and stuff around. There's the option of using some like CPU coolers for PCs, gaming PCs and stuff, instead of having a big old bucket of water that I think would be fine. So I'll keep investigating that. But that was kind of one of the modifications that I think was a good idea. I haven't seen that done like this. Pretty easy. These fittings are pretty affordable and pretty easy to put on. They're just compression fit. In fact, they're the sleeve kind where you slip on the little compression fitting and then tighten the nut. There's no tube flaring or any of that old copper plumbing stuff that needed to be done. There's probably many other ways to do this as well. This was just the one that came to mind and seemed kind of easy. But anyway, that's pretty much it. I'll try to show it also once I get it all done and a little bit more buttoned up and actually show it heating something up. But for now, that is the overview of the system, and I'll also try to give a little wiring diagram to show how it all connects together. So anyway, hope this helps, and yeah, I'll try to post more.